Hello, how are you all doing today? We are Memphis Communiversity. We are practicing some AP Calculus free response questions. We're doing my favorite topic, differential equations, and we're at difficulty number 5 out of 10. So we're getting up there in terms of progressing as we do these. Difficulty number 5, this video is a little bit unique in terms of our videos. Of course, we're going from difficulty 1 all the way up through difficulty 10. So continue with us as we continue that journey. But difficulty 5 is going to be the one differential equation free response question, or maybe there will be another one in the future. But for now, we're not going to have any separate and integrate on this question because there's enough to ask without having a separate and integrate question. Really, we're going to be focusing on the non-separated integrate questions in this free response practice. Keep in mind that there is going to be a BC question at the very end. It is Euler's method, but hopefully those of you that are AB still stick with us because part A, B, and C would be on the AB exam. So again, sometimes on the BC exam, when you have a differential equation free response question, they sort of avoid doing separate and integrate because there's enough things to ask without separate and integrate. So let's get started. It's still a differential equation, frick. So still the given is dy dx, this equation that involves derivatives. We do have a particular solution, but we're not going to use it to find plus c's or a's or anything like that. Because we're not going to do separate and integrate in this question. This is non-calculator, like usual. So let's get started. Keep in mind that because this is not separate and integrate, it's going to be, again, sort of the miscellaneous topics on differential equation, free response questions. The videos that I would suggest watching especially would be a video, I believe, that is called Differential Equation Miscellaneous Topics on our channel. It goes over how to take second derivatives of differential equations and how to do relative min or max and how to do L'Hopital's. So check that out. And then, of course, you can check out our Euler's method video as well. But let's just get started in terms of this question. So we have dy dx. And then the first question seems pretty harmless, but it's pretty tricky in my opinion. What we need to do is we need to find the second derivative. So we're given the first derivative. We need to find the second derivative. Of course, that involves taking another derivative. Just one derivative, though, because we're starting off with dy dx. So let's write that down. And then this was given. And what we want to do is we want to take the derivative of dy dx. So we're going to write dy over dx squared. This is the second derivative, of course, written in Leibniz's notation. And we're just going to take this derivative once and we're going to be done because we're starting off with the first derivative, ending on the second derivative. So the only thing that's a problem with this derivative is, let's take the derivative of x cubed first. That's pretty easy. That is just the power rule. So it's just going to be 3x squared. But it's this last part that looks pretty harmless, but a lot of students do mess it up. It's very easy to mess up. You can't blame them for messing this up. So a lot of students, when they take this derivative of minus 2y, they just write minus 2. Because they're like, well, the derivative of 5x is 5. So y is not the derivative of 2y. But y is a function of x in this case. So when we take the derivative of y, we need to do the chain rule. This is called implicit differentiation. So when you take the derivative of 2y, it's actually not 2y, it's 2, and then times y prime. Then I wrote y squared, but y prime there. So again, another example of this is the derivative of y cubed, for example, would not just be 3y squared, it'd be 3y squared times y prime. The derivative of sine of y is cosine of y times y prime. Just keep in mind that we did need to use implicit differentiation here, what I call impdiff. And also, it's even harder to spot in other questions. So, for example, I believe in our last video, we had something with a different variable. So just be careful if you have something like, I don't know, D, let's say, what's a good letter? Let's say K or something over dt, and you have like the first derivative is 5k. So we're just doing a question on the side just to hammer in this point. When you take the second derivative, k is like y, it's the dependent variable. T is like x, it's the independent variable. So the derivative of 5k is not just 5, it's 5 times dk dt. Another thing to say is that you don't have to write y prime, you can write here dy dx. So But again, just be careful with these implicit differentiation questions. They are pretty easy, but they are easy to mess up as well. Just keep in mind, what is the y in this case? What is the x in this case? Derivatives of x are regular, derivative of y's are not regular. But this question says find the second derivative in terms of x and y. We have the derivative in terms of x squared and y prime, so we are not done yet. But all we have to do is one final step. This thing is y prime, dy dx. One is y prime. That's the same thing as dy dx. So all we're going to do is we're going to replace y prime with x cubed minus 2y. So we're going to get 3x squared minus 2 times x cubed minus 2y. And we are done. So we're just going to box this guy. This is our second derivative. So again, it's just implicit differentiation. So for example, in this one that we did on the side, if we needed to, we would replace dk dt with 5k plus 1. So this second derivative on this question, which was of course extraneous, but this derivative would be 25k plus 5 once you simplify. So just be careful on these questions. It is implicit differentiation. They're trying to get you, but we are better than that. So let's do this next question. Does the graph of f of x have a relative minimum or relative maximum, or neither, at this point 2, 4, and then we have to justify our answer. So when I think about relative or min or max, when I see those words on the AP exam or whatever calculus class that you're taking, that you have the pleasure to take, what I think of immediately is what is called the first derivative test. So we'll put that in the corner here. And that's the test that you use all the time, basically, for relative min or max or local min or max. So remember that a rel min is when f prime goes from negative to positive. A rel max is when it goes from f prime goes from positive to negative. So this occurs quite often, especially in graph free response questions. Check out our videos on those. They occur just throughout the multiple choice as well, just finding a relative min or a local min. What you want to do is either graph f prime with a calculator, or just look at the graph if it's provided, or provide the graph of f prime or a sign chart of f prime that you drew. So my first instinct every time when we see these sort of questions is, well, I want to find a sign chart of f. But unfortunately, f prime is this, and it involves two variables, so I'm not going to be able to draw the sign chart of f prime. So basically, I needed to have an alternative way to find relative max or min in this case. I'm not going to be using the first derivative test. So you might be asking, what is that alternative going to be? Well, I'm actually, if we're careful with the question, they're actually giving us a hint. Basically, they ask us to find the second derivative, and then they immediately ask afterwards whether we to find a relative min or max, and that's because there's a alternative way to find a relative min or max, which is the second derivative test. So the second derivative test, what it says is, it's a little bit opposite of what you might expect. What it says is, if f prime equals 0 and f double prime is positive, that's a relative min. That's because if you have a function that looks like a min, and you have a 0 here, so it's a horizontal line, that's the f prime equals 0 part. This would be concave up, so you want f double prime to be positive, so positive does go with min. It's a little bit confusing, but it makes sense if you think about concavity. And then the opposite is true. If it's a negative, that's a rel max. So this is the test we're going to use, because in this test, for the second derivative test, you don't need to find a sign chart of f prime or f double prime. What you just need to do is plug in the single point 2, 4 into f prime, make sure it's 0, and then to plug it into f double prime, see if it's positive or negative. Again, positive goes with rel min, negative goes with rel max. So before we do that, let me just stress this point again. If you ever take a second derivative, if they ever ask you to take a second derivative, and they immediately ask you to find a relative min or max, they're telling you that this is probably the second derivative test. This is a way to force you to do the second derivative test. Your first instinct should be the first derivative test, but if that doesn't work, you move towards this alternative, which is the second derivative test. So hopefully that makes sense. This is one of the ways where on the AP exam, you are forced to take the second derivative test. So I never do it almost voluntarily. I do it when I'm basically forced to, which is when they ask me a second derivative. So I'm like, oh, they're probably making me do the second derivative test. And I can't draw the sign chart of f prime. This occurs also in Taylor series for responses for those who are in BC. For example, they occur when you have the Taylor polynomial and you know the second derivative, but you don't want to draw the sign chart of the entire Taylor polynomial. So that allows you to also find relative min or max. But let's apply the second derivative test in the context of this question. So what we're going to do is we're going to take dy dx. So hopefully you can read this. Dy dx just is x cubed minus 2y. We are going to plug in the point 2, 4. So hopefully you understand how to plug in these points. So this is not a negative, it's just a regular 2. So what happens is you're going to plug in 2 for x and then y for 4. That's what this vertical bar notation means. So notice you do get 0 because you get 2 cubed, which is 8. 2 times 4 is 8. 8 minus 8 is 0. Then we're going to plug in this point 2, 4 into the second derivative, which is why they asked me to find it. So I can conveniently use it. Sometimes this is a given in the original question, and then you're like, oh, why are they giving me the second derivative test? It's probably second derivative. It's probably to employ the second derivative test, maybe to tell if something is tan line is an overestimate or an underestimate when you approximate, and we'll have videos on that later. But for now, what we're going to do is we're going to plug in 2, 4 into this guy now. So if you look at here, this is the same thing as dy dx because we replaced dy dx with this thing. So this in the parentheses, that's going to be 0 again, 8 minus 8, so 0 times minus 2. So basically when you plug in 2, 4, the only thing that matters is right here. 3 times 2 times 2, I believe is 12, so this is greater than 0. So we go to the second derivative test. This implies that we have a relative min, because again, this implies that it's concave up. There's a horizontal tangent line, that's what the first derivative equals 0. And so we have a relative min here. So we have a relative min. I can't fit the word minimum, so I'm just going to write relative min. Keep in mind, though, that the second derivative test, while its name is the second derivative test, because it does use the second derivative, you do need to verify that the first derivative equals 0. So the second derivative test actually involves both the first derivative and the second derivative. Why is the first derivative involved in the second derivative test? It's because you need to verify that this thing has a horizontal tangent line. That will rule it down to either a rel min or a max if the second derivative is positive or negative and not 0. So, these two questions sort of came in a pair. We took second derivatives carefully with implicit differentiation, and then we found a rel min or max using that second derivative by using the second derivative test. So hopefully that all that made sense. Let's go on to the next one. So we still have the point. Let's write out the givens real quick in the corner so we don't have to flip the page. So f of 2 equals 4, and the differential equation, I believe, is going to be x cubed minus 2y, sorry. So we have that information. So here we have a limit. And while it's not true in every case, and every time you see a limit, you have to think of the possibility, oh, it might be a L'Hopital's rule, because that is one of the main limit properties, limit ways that we can do it. And remember that L'Hopital's rule is added to the AB exam, so anytime you see a limit on the AB exam, it's probably going to be L'Hopital's rule. I believe that while L'Hopital's rule was added to AB, to the AB version of the exam, it still has not been asked in the context of a differential equation free response question. But in the past, L'Hopital's rule has been asked in the context of a differential equation with L'Hopital's rule. So I imagine that within the next few years, this current year being 2020, that eventually there will be a differential equation free response question on the AB exam. Perhaps it'll be AB and BC, where you'll have to do L'Hopital's in a differential equation with this information. So I think this is a good question to do. So let's do it. So it is a free response question, so you do have to write L'Hopital's rule in a little bit of a precise way. I have the urge of writing 0 over 0, but they really don't like that. So I'm going to write it in the FRQ way is what I call it, the free response way. So let's do that here. So what you have to do is you have to verify the limit of the top equals 0 and the limit of the bottom equals 0. So we have limit as x goes. So hopefully you can tell what my limit is. I write it very fast and messedly, but this is limit. So we need to verify that these two limits are equal to 0. Let's take this one right here because it looks easier. So when you plug in 2 here, you'll get 4 minus 8 plus 4. That'll be 0. 4 plus 4 is 8. Minus 8 is 0. And then let's take this one. So some students get confused because they're like, oh, I don't know, I have a G here. I really should have an F. Sorry about that. A little bit of a mistake there. So I have an F here because we're dealing with F. I don't know why I use G. So hopefully you don't mind that, but we have f of x here. So some students get confused how to plug in f of x, how to plug in 2 here. It's easy to plug in 2 into this one, and it's harder to plug in 2 into this one. Well, if I had written the correct function in the first place, actually it's pretty easy to plug in f of 2. It would be very hard to plug in g of 2 because we have no idea what g is, but f of 2 is pretty easy. Keep in mind that we're going to use this given point. So f of 2 equals 4, and 4 minus 4 is 0. Another thing to keep in mind is that if the limit was written correctly in the first place, this information might be above the free response question, like it might be in part just right here. So just keep in mind, you'll use this given point and the differential equation potentially in every single subpart. So just look around, even if it's not given for the particular subpart question, you might be using the original givens. But it does look like we have 0 over 0, so it is time to lope that tall to apply L'Hopital's rule. So by L'Hopital's rule, we have 0 over 0. Then what you do is you write the original limit. And then you write a limit with the ratio of the derivatives. So I avoid writing 0 over 0. So I'm going to write limit x goes to 0. Well, what's the derivative of f of x? It's f prime of x. And then what's the derivative of the bottom? It's going to be 2x minus 4. And then what we do again is we're going to plug in 0 and 0, not 0 and 0. We're going to plug in 2. So I don't know why I wrote 0 here. It's 2. So we're making a few mistakes in this L'Hopital's question, but that's really how math works. You're going to be making some mistakes throughout. So don't feel bad when you make mistakes, because know that I make mistakes, and every student that I've ever had made mistakes. So let's plug in 2 here. So when we get 2, well, it's going to be a little bit tricky because it looks like when you plug in 2 into the bottom, you're going to get 0 because it's 4 minus 4. And then also, again, some students get confused on how to plug in 2 into f prime of x. They don't see an f prime of x, but remember that dy dx is equal to f prime of x. So we're going to plug in 2 here. Again, students get confused because they don't know what to plug in for y, but we plug in 4. So we get 2 cubed minus 2 times 4, which is going to be 8 minus 8. So unfortunately, or maybe fortunately, this is a double L'Hopital's question. So what we're going to do is we're going to lope that tall once more, which means we have to do the same thing and rewrite all of this. So we're going to write because the limit of the new top is equal to 0. The limit of the new bottom is equal to 0. We're going to write by L'Hopital's rule. And then we're going to write this new original limit. (2x minus 4). And now we can take the derivative of the ratios, or the ratio of the derivatives. So that's going to be limit as x goes to 2. I actually did the first one already, so that's f prime of x. Again, mistakes are perfectly fine as long as we allow them to improve ourselves. So the derivative of f prime of x, again, this is the same limit as this. So we're doing L'Hopital on this process. We're loping that tall, is what I say. The derivative of f prime of x is f double prime of x, and the derivative of the bottom is 2. So it looks like we're not going to have to do L'Hopital a third time because we have 2 on the bottom. But the question is, how do you plug in f double prime at 2? I don't see any f double primes on the page, so I'm having a little bit of a panic. But remember that in the first question, we were forced to take the second derivative. So let me rewrite that second derivative. It was 3x squared, so this was dy. It was kind of right sideways here. 3x squared minus 2, I believe. And then dy dx. So we are now going to plug in 2 into the second derivative. And again, there is a y here, but we're going to plug in 4 for y because the point is 2 comma 4. Remember that when we plugged in 2, 4 into this parentheses, it was 0 because we got 8 minus 8. That canceled all of this stuff. So we're just going to plug in 2 into the top. So that's going to give me 12 over 2. And we are finally done because this is 6. So this is how you do L'Hopital's rule. Not the hardest question in my opinion. You just have to be careful and you just have to know how to find derivatives. And it's actually easier than normal because derivatives are either given or you already found them. Just keep in mind that this is the precise way to do L'Hopital's rule. Limit of the top equals 0, limit of the bottom equals 0. By L'Hopital's rule, original limit equals new limit. Don't feel bad if you make mistakes. Everybody does so, and mistakes are part of the process. We're just trying to get better. So if you have been watching and as an AB student, I applaud you because I hope that you gain something out of this. But for now, this is a BC topic. This is Euler's method. One teacher mentioned to me once that Euler's method is probably the most likely thing to be added to the AB exam. So perhaps if you're watching this in the future, it might already be on the AB exam. But as of 2020, it is a BC topic. And it's one of those BC topics that is actually easier than a lot of the AB topics for some reason. I don't know why it's not just on the AB exam. Something like arc length as well is pretty easy. Logistic is not that bad. It's the harder stuff like series and Taylor series that makes BC harder. But for now, let's do this question. So I'm not going to explain Euler's method in terms of why it's true or sort of what exactly you're doing. I'm just going to explain the process. And then if you want, you can watch our videos on Euler's method. I think we have 2 of them, one by myself and one by a former student. Check it out on our page. Hopefully it's there by now, by the time you watch this, where we practice a lot of Euler method questions. But for now, what I like to remind my students is that the general process is you want to find a new y or the next y. And what it is it's the previous y. So the word previous. Can you tell that's the word previous? I'll mark it out first now. So it's the word previous y. It's basically just a line where you bring over, it's like y2 minus y1 equals slope. So it's step size, plus, struggling now, step size. And then what you do is you plug in old x and old y, or the previous x and the previous y into slope. So slope of previous x and y. Again, it is just the equation of a line. Slope is equal to y2 minus y1, but we brought the previous y over, so we added it over, divided by the step size, and the step size is x2 minus x1. So this equation isn't too bad. It's just the equation of a line. But let's just do Euler's, and then we're going to be done. So just like in the previous ones, the differential equation is important. So we'll write that out. The only thing that people have trouble with in Euler's is a lot of times it's fractions. So just be careful with fractions. I made the question so that I don't have to deal with fractions because I don't want to deal with them right now. But just these questions are, again, usually non-calculator. So just be careful when you're doing fractions. If you have decimals, I would change them to fractions, but that's just me. Perhaps you like using fractions more than decimals. But let's get started. I think this one shouldn't be too bad. So I like to write out x is equal to 2 and y is equal to 4. This was the original point. That's where I'm starting. And then I'm going to do 2 step sizes. So it looks like I'm going to 0. So it looks like I'm going to have to go to 1, and then I'm going to have to go to 0. So this will be my first step and then second step. So it looks like the step size, I don't know why it's written as an h, but it's usually written as an h. Keep in mind that it's not just 1, it's -1. So that's one small thing because we're going backwards. We're starting with x equals 2, going backwards to 0. And let's just employ Euler's now. So what we're going to do is just use this sort of formula right here. So it's the previous y, which is going to be the number 4, plus the step size, but we're not going to write +1, we're actually going to write -1. So -1 times, and then we're going to plug in the previous x and the previous y into this equation. This is not going to be the best question now that I look at it, but I'm sorry about this, but this is still a valid question, so we're going to continue forth. We're going to plug in 2 and 4. So you're going to get 2 times 4 times 8 minus 8. So we've done this before. This is going to be -0. So as you can tell, we actually just get 4. The next step is just 4, but that's perfectly fine. That's just how the question worked. So we're going to now ignore this one, and now our previous x and our previous y will be 1 and 4. So in this case, I don't think we're going to get 4 again, so let's do it. So again, it's the previous y, so it's not going to be this number, it's technically this 4, because the previous y is this 4. The step size is still -1, and then we're going to plug in the previous x and the previous y into this equation. So it's going to be 1 for x, so that's 1 cubed, that's 1, minus 8. 1 minus 8, I believe, is -7. So we're almost done. 4 times -1 minus 7, that's just 4 plus 7, which of course is 11. So that's Euler's method. The only thing tricky about this Euler's method was that we were going backwards, so the step size was negative. But a lot of my students, once they learn Euler's method, do prefer to have it on a differential equation free response question, because it is the same process every single time. It's an easier process than, for example, separate and integrate, which are also on differential equation free response questions. But just remember that if you're to deal with either fractions or decimals carefully. So we're actually done with this free response question. It is difficulty 5, and it's not difficulty 5 in terms of the processes, because the processes themselves throughout this free response question, hopefully you could see that it was not too bad. There were just a little small things here and there which made it, which gave us the opportunity to make several mistakes, which of course I did. So just keep in mind these small little tricks. So let me remind you of them. When we took the second derivative, we started off with the first derivative, but when we took the second derivative, we need to employ implicit differentiation, which means anything that had y's needed y primes. Secondly, we had to do a relative max or min question. Because we were asked the second derivative, and the first question, it made sense that it was the second derivative test, which is much rarer used than the first derivative test. But here we're forced to use the second derivative test. And remember that the second derivative test says if f prime equals 0 and f double prime is positive, that's a relative min because you're concave up. And the opposite is true for a relative max. So in this case, we had a relative min because the first derivative was 0 and the second derivative was positive. This question was a L'Hopital's rule question. Pretty standard stuff. Just remember that you're going to be using these givens throughout the free response question. So throughout this particular subpart of the free response question. So if ever you need to find, for example, f of 2 or f prime of 2, you use this equation, or even f double prime of 2. And for this L'Hopital's rule, we did write it carefully. We did it the quote-unquote the frick way, or the free response way. What you have to do is not write 0 over 0. You have to write limit of the top equals 0, limit of the numerator equals 0. By L'Hopital's rule, original limit equals the limit of the derivatives. The ratio of the derivatives. I never can say that phrase properly. And of course, because this question was so much fun, we had to do it again. And then finally, we had Euler's method, a very standard Euler's method question. This is the formula for Euler's method, where the only thing that was a little bit iffy was that the step size was negative because we were starting at 2 and going to 0. So I'm hoping that this was useful for you, even if you were an AB and you did stick around to the end. I applaud you, and I am happy that you did so, because it's nice working with friends, you know. But we are going to be continuing the series. This marks the midway point, and the free response questions after that will be slightly difficult. But again, it's really heavily dependent on the separate and integrate question, in my opinion, if you can recognize that when to do that. So stick around for the second half of this video series as we go from difficulty 6, difficulty 7, difficulty 8, difficulty 9, and difficulty 10. I will see you there. Thanks for watching, and see you soon.